So thank you for joining me to listen my lecture on harmonic waves. So that's the third lecture regarding the wave motion on the course of optics. So what I will do in this lecture is that I will try my best to introduce to you a concept of harmonic waves. So essentially harmonic waves are the simplest possible solution into the wave equation we have just derived. And I will now in practice show what really exactly is the functional form of a harmonic wave. So basically we will show to you that it's either a sinusoidal or cosine-like function, the wave that we are describing. And this of course then means that the harmonic wave that we are dealing with is a periodic in nature, because we can calculate the derivatives of sines indefinitely, and this actually implies quite a bit for the properties of the wave. And this also allows us to derive the propagation constant for the wave. So essentially that's the amplitude of the wave vector that we're dealing with. And we also know that the harmonic wave is periodic with respect to the time, and this gives us a possibility to define what is the frequency of the wave and what is the velocity of the wave. And then I could define again the angular frequency that we already discovered in the chapter 2. And finally, I will generalize the treatment a little bit by introducing to you a concept of initial phase that then allows us to adjust the phase of our wave also at the origo of our coordinate system. So that's what we will be doing in this lecture. And I will just now get started the treatment. So we are considering harmonic waves. And this is a very important class of a wave. So in a way, this is a special case. This is a mathematical construction. We cannot physically realize harmonic waves ideally in the lab, because it's a idealization of situation. This is something that we cannot never achieve in real life. But at least it's a good representation because it's simple. And then later on, when we take use of the superposition principle, we can actually start forming something that is more realistic by just summing many harmonic waves together. And this is the important starting point. This is a solution of the wave equation. So we can already learn a lot of physics by just dealing with harmonic waves. This shows the picture, what happens. So we have a sinusoidal oscillation. Wave is propagating along the positive z direction. And after a while, the wave starts repeating itself because, of course, we know a sinusoidal function is periodic. Harmonic waves are described by harmonic functions. That's the name. And harmonic functions are also known as the sine or cosine functions. And this, of course, means that they are periodic in nature. And roughly the waves are of form psi. Again, we have two variables of interest here, propagation direction z and the time coordinate t. And the wave psi, the functional form of the function is that the argument is of form z minus vt, so that the wave actually propagates at the speed of v in the positive z direction. And as we already outlined in the first of lectures, this is form A, where A is the amplitude of the field. And then we have a sinusoidal modulation, sinusoidal oscillation of the wave, and the argument of the wave, the phase of the wave is of form K, the propagation constant, times Z minus Vt. And that's the argument. And the sinusoidal functional form essentially gives us the phase evolution of the wave, so that the wave then starts oscillating when it's propagating, or when we look at a given position and let the time flow, then the wave oscillates also with respect to time. So this is what the sinusoidal function here gives us. And this is the harmonic function. And since we have this kind of simple dependence on time and spatial coordinate, we speak of this as a harmonic wave. So A is the amplitude, and the argument inside the sines, this is the phase of the wave. The parameter k, also known as the propagation constant, the amplitude of the wave vector, tells us how quickly the wave then oscillates as a function of the direction of propagation z. And now what we will do next is that we did this already in the lecture on chapter 2, but we will kind of derive what is the propagation constant, where it arises, and we see that it arises from the periodic nature of our wave. So we start by just looking at the wave at the instant of time equals 0, and then the wave is of form that time t equals 0, that it's simply a times sine of k times z. So this is the exact form of our harmonic wave. And now we will take use of this functional form, this function for the wave or representation of the wave, and we will define some important properties, and that's how we will proceed in this lecture. So what we will want to do is that I want to then derive you what is the propagation constant. I will redefine what is the period of the wave, and how do we get the velocity of the wave, and how do we relate that with the wavelength and frequency of this wave. And then we go into the definition of the angular frequency. and these are really helpful to understand well the main properties, the basic properties associated with the waves, because all the rest of our treatment is using these concepts. So, harmonic wave, sinusoidal function, of course, it's periodic. So what this means is that it repeats itself after a given distance, also after a given time, but let's look at the distance first. So when the wave has propagated to a distance of lambda, where lambda is also known as the wavelength, of course, from the mathematics, we see that after this propagation distance, z plus minus lambda, we should repeat itself. The wave should repeat itself. So we have this equality between the location in z, and when we go, for example, 1 plus direction of wavelength along the positive z direction. So this equality must hold. And this is the way how do we define the wavelength for this harmonic wave. We plug in the actual forms for the waves, and we get this kind of equality. So we have the a's on both sides, we can vanish them, and we have the two arguments inside the signs. And essentially, if you want to equate things, we can let t to be equal to 0. We have a condition that the k, the propagation constant, times lambda, the wavelength, must be an integer of 2 pi. So m here is an integer. So when we choose the smallest possible of k's, we choose m integer equals 1. And then in this case, our propagation constant, also known as the amplitude of the wave vector, has a simple form of k equals 2 pi divided by the wavelength lambda of light. And here the k, it's also known as the wave number or the wave vector, or to be more precise, the amplitude of the wave vector. So this is how we define the propagation constant k. And now, like I promised, we next look into the periodicity of harmonic wave with respect to time, t. And of course, after a while, the wave starts looking back exactly like itself, original self. So we call this period of time with the tau, and terminology is that's the period of the wave. And similarly, of course, we have a wave, and after this kind of oscillation time of t plus tau, the period of the oscillation, we have equality, so that the waves should look exactly as at instance of t equals t. And now what we have is that we have a condition that the k times v times t must be an integer of 2 pi times m, where m again is an integer. And from here, we can actually relate the period tau with the wavelength of light, lambda, and the speed of light. And here t is the period of our wave. Now, what we see is that the wave, the harmonic wave that we have and are dealing with, it oscillates with respect to time. And since it oscillates, we can also define a frequency nu that tells us how quickly the wave oscillates. So the nu can be defined that it's the 1 over the period, and this being equal of taking use of the earlier equation is that then this is equal to v times lambda. And sorry about the typo, it should be w here. I'll fix that into the actual notes. So the velocity of the wave v is then simply given by v, velocity of light, equals, or wave equals the wavelength of the wave times the nu, the frequency of the wave. So this is what we get from this derivation. So now we already have equation for the velocity with respect to the wavelength and frequency, and that's quite nice because of course we know that the velocity of light in vacuum is a constant. So now we can already then relate, once we know what is the speed of light at vacuum, we can relate the wavelength with respect to the frequency. Now, like I already said, usually, especially in this course and our framework, that the kind of mathematical framework we're using in most of our courses, we don't really deal with frequency nu or f that much, but rather we use a so-called angular frequency omega, and omega is defined as a 2 pi multiplied with nu. So this is the angular frequency. Please remember the definition, and this is most of the time the frequency that we use in our courses. There's also a parameter, a way to define things further, is that we could also define a similar quantity, spatial frequency, kappa, which is then defined as a inverse of the wavelength. And in some fields, subfields in optics, if I remember correctly, in spectroscopy, this spatial frequency is sometimes also known as the wave number. So please be warned that depending slightly on the context, it might be that the terminology is a little bit ambiguous, that it might be that the wave number might have a slightly different meaning than we are using in our course. But here, there's no confusion in this course, so don't be fooled by this. If we are using a concept of spatial frequency, we are calling it spatial frequency, and the wave number is something else. So we do have the 2 pi over lambda definition and not just 1 over lambda. And with these definitions that we have, we can now also define the phase of the wave. And the phase of the wave, of course, it's the argument we put inside the sign. So that was equal to k times the z minus vt term. And we can multiply k inside the parentheses. So then we have equal to a case of k times z minus kvt. And then we can change the velocity of light v in there to be described using the frequency nu and the wavelength of light. So essentially here v equals nu times lambda. So we can change the latter term. And now what we can do afterwards, we can change this latter thing to the angular frequencies. And we see that the phase, the argument of sine can be just simply written as k times z minus angular frequency omega times time t. And in this case, we can just simply write the harmonic wave into a form that psi equals a, the amplitude of our wave times the sine, and inside the argument we have just simply this kz minus omega t term. And I prefer this because it's quite symmetric, and this is somehow easier for me to remember what is the functional form of my harmonic wave. Now, we're almost done. What we are left to do is that we generalize the approach slightly. And why we need to do this is that the phases of the waves that we have considered so far, they have been restricted, that when we are at the origo and when we are at the time equals 0 case, the phases are also zeros. And of course, this is a little bit limiting the case because I could easily imagine that there would be waves that have a more arbitrary phase at that given location, at that given instance of time. So of course, we need to generalize our mathematical treatment. And this can be simply done by just introducing to you a concept of initial phase, epsilon, for the wave. And this then gives us a wave function of form psi, now equals the amplitude a times sine. And now inside the phase term, we have the similar kz minus omega t, and now plus the initial phase. And this is the initial phase that then adjusts the phase, the original phase of our wave. And here the phase epsilon, if it is not 0, then of course the initial phase is slightly different. And this has been clarified in the figures from the booklet and hopefully this introduces to you clearly what we can now do. In the original case, we're restricting our wave to have a given phase, specific phase at the origo at a given instant of time t equals 0. And now when we have a initial phase epsilon that is not 0, we can actually adjust what is the phase in here. And this is absolutely what we need when we start actually summing many waves together, because we really need to be adjusting the relative phases of the different waves, because that either gives us constructive interference or destructive interference. And needless to say, almost that we could equivalently just describe everything using cosines. So my wave could simply just equally well be A, the amplitude, times a cosine, times the argument that we have already described. And now I just have epsilon prime in there to just clarify that in this case, if I would want to have physically exactly same kind of wave as an outcome for the math, of course epsilon prime must be different than the original epsilon if I use sines. But any case, I could equally well just use a cosine representation for my wave. So this is what I had in mind to say about harmonic waves. I hope it was helpful for you to go through this lecture. And next lecture, we will be generalizing things slightly. So more, we will be looking into the phase term. So what is inside the argument? And from that, how we can, for example, derive a concept of phase velocity, a parameter of phase velocity, and how that relates then to the propagation speed of the harmonic wave. But more on that in the next lecture. Thanks and have a good one. Bye-bye.